for inviting me. So this talk is going to be kind of very much in the same vein as Ray's talk. We want to be able to learn some sort of natural language semantics without cheating too much or using less supervision, as I would put it. So to be more concrete, let's take a look at the problem of question answering. Suppose we build a system to answer questions like, what is the largest city in California? Okay, so actually with this question, these days it's not so hard to get an answer. You just go over here to, oh no, what happened? You didn't see anything? No. Okay, so if you type it into your favorite search engine, which of course is Google, then it actually not only gives you the answer, but you see a lot of, basically the answer is written all over Los Angeles is the largest city and here everywhere. Okay, so that's maybe a kind of a solved problem in some sense. But what if you wanted to know what is the largest city in a state bordering California? Okay, so let's go to our Google here, and what do you think is going to happen? So you get a lot of results about Union states and bordering, but you don't really see anything resembling the answer you want. Right, and what this illustrates
is Las Vegas or Phoenix or what?
It's Phoenix. So this is just to illustrate that we're interested in, I mean, ultimately we're interested in language understanding, and real language understanding requires more than just kind of a superficial matching of keywords. It requires you to take apart the sentence. So let me show you a demo, which is the system that I'm going to describe later. Is able to handle these type of more complicated ways. So let's just begin with something. What is the largest city in California? And this better work, otherwise embarrassing. Okay, so what the system does is it's going to take this sentence, it's going to parse it into an internal representation, which it's a label, a tree structure with some labels on it, and then this is a logical form or a program, or if you want to think about it, even a SQL query. It's evaluated with respect to a database of facts about US geography, and the answer is displayed above. And one thing I want to point out is that we're going to be inducing semantics. So this is the semantics of the sentence, but we're never going to observe these. Instead, we're going to observe just the answer. Okay, I'll explain what the tree is and how the learning works later, but just to kind of get a feeling for capabilities. So what is the largest city in California? What is the largest city in the state bordering California? That's better work too. Okay, so it gets Phoenix, which confirms Ray's answer, and you can compose it. So you can say what is the population of, try this one. And then so these facts are a little bit old, so Phoenix has more people now. But the idea is that because we're kind of analyzing the actual language, you can make this fairly complicated, and it kind of composes.
When we try state bordering the state, that bordering the state, that borders the state.
It probably wouldn't be Los Angeles. Yeah.
Yeah, you're right, because you get this transitivity.
Yeah. Okay, so so now I'm going to go more into the details of what we're doing here, but just to kind of illustrate the point, what is the nature of this problem that we're trying to solve? We're going to be learning, but the model we're going to be learning is very, different from a lot of machine learning that you might see on text. So take, for example, a document classification. Here, the input is a document, output is a category. And here, learning isn't terribly difficult because all you have to do is learn these associations between the words and the category, and you get enough training examples and you learn these correlations directly. But if you look at the problem, if you really want to understand a sentence, here's the input and here's the output. Here you can see that there's no superficial correlations you can exploit. There's something deeper going on. So let's try to kind of work through what this is. So I'm going to write some kind of logical form looking expression, but just give you the intuition. So this is definitely talking about a city. Let's call the city C, and the city is in some state S, and the state is border of California. And if you take the largest one of these with respect to the population metric, then you get this. And if you evaluate this on your database, you get the answer you want. So notice that there's this kind of important thing, that there's computation that has relatively complicated. It is kind of executing something on a database that separates the sentence and the answer, and furthermore, it's unknown, so we're going to have to induce this kind of nasty expression. So the first theme of the talk is a program representation. So I'm calling these programs or logical forms or SQL queries, whatever you want. But the idea is that you want something fairly structured to be able to capture the complexity of language. And another theme is that given that you want to use these data representations, how do you learn them? And as Ray mentioned in his talk before, a lot of methods go and say, here's a sentence, I'm going to label a logical form, but this requires an expert, someone who knows how to read and write these logical forms, and there aren't that many experts out there. So from a kind of scaling point of view, this you can't get too many sentences this way. We're going to try to learn from what I call natural supervision, which is you just get question and answer pairs. And this form of supervision just requires a non-expert. So you can put this on Turk, you can give it to your grandma, and anyone who has access to the facts can provide this form of annotation and the skills. Another point is that this form of supervision is kind of dependent on your representation, and if you are trying to build a question answering system, in some sense, what your ultimate goal is the answer. So in some sense, this is providing you the full pipeline rather than stopping it somewhere in between. So natural supervision, I'm just kind of using this term loosely, is where it's kind of more from a data collection point of view. Natural supervision, which is I call natural supervision data which you can get from non-experts. So this has been very useful in other places in NLP, for example, machine translation, where machine translation systems learn from examples that look like this. You have an input sentence, you have its translation, but importantly, you don't get how the translation happens, that city is viewed and so forth. That's kind of inferred as a latent variable, and it's been very successful because you have a lot of data that looks like that, and basically no data that has more detailed supervision. So if you can exploit it, then great. But it also creates a harder learning problem, so we're going to have to deal with that. Okay, so there's the two parts, program representation and natural supervision, that are kind of the key kind of themes and ingredients that are going to make this work. Okay, so in the rest of the talk, I'm going to go in more detail about how this works. Any questions so far? So first, I'm going to talk about the representation, right? So I drew some trees, and then I wrote some logical form-looking expression. So what is this latent variable actually going to be? So there's a few considerations. One of them is computational. What the learning algorithm sees is a question and an answer, and it kind of has to, infer this linked variable. And there's a lot of different things that this could be. Most of them are incorrect. They don't yield the answer that you want. And one of them is correct, or a few of them are correct. So the landscape looks like you have a sea of incorrect logical forms and maybe one or two different logical forms, and you kind of have to find these. So it's a kind of a hard search problem intrinsically. But even if you know, if I give you this logical form, there's still the statistical question. How do you parameterize this mapping from sentence to logical form? This is kind of the classic problem. In linguistics, it's compositional semantics. Kind of from a learning perspective, it's kind of more of a call it parameterization because it's how you parameterize your model. So, just to kind of harp on this a little more. So it's not clear, that kind of city corresponds to city down here. By the way, I'm using italics to denote words, which are going to be distinct from these symbols, which could be, this city could be XYZ 1, 2, 3, for example. So this mapping is non-trivial. So what we're going to do in this talk is I'm going to talk about a formalism or a framework which I call Dependency-Based Compositional Semantics, which is a particular way of representing semantics which has a number of advantages, which I'll show later. And the idea is that the logical forms are going to look like this, and intuitively you can think of taking the words, forming a dependency tree, and replacing the words with these logical predicates and putting some labels. See how this kind of works out in a bit. I'm going to formulate a little bit later, but there's one kind of important piece missing, which I've kind of glided over, which is where are the answers coming from? This is just kind of understanding the question. In order to answer the question, you also need to know the answers. Like for example, what is the largest state bordering what is the largest city in a state bordering California? I'm sure all of you understood the question, but you might not have the answers. And here we're going to assume we have just a database of facts. In this case, US geography, but more generally about other things. And a database looks like this, where you have, for each predicate, you have a set of tuples of things. For example, this says San Francisco has the relation log with California, and so on. So it's fairly straightforward. Okay, so now, given this database, yes?
Is that to say that the relations that you're going to use are also specified for the database?
So these symbols are fixed in advance, and the contents of the database are also fixed. I'm not doing.
So I noticed in the previous slide, for example, you had argmax, but that's not in there, obviously, right?
Right. So you, that's a good point. So conceptually, you can think of argmax as one of these predicates, and it's, if you were to write on the table, it would be a set and like the largest element of that set.
Okay.
So we should notation, it's just a predicate. So it's implicitly represented. Okay, so now, given one of these DCS trees, which are these logical forms, and a database, I'm going to tell you what this actually means. So no, we're not considering the language here, just considering how you interpret this. Okay, so the idea is that a DCS tree encodes a constraint satisfaction problem where each node introduces a variable, and each edge introduces a constraint, and each variable also introduces a constraint. So here C is a variable that's an element of the cities, as a set of these pairs, and you have constraints like the first element of C, so C1, that's what this one corresponds to, is the same as L1, which is the first column of this table. So you have this system of constraints, and one of the solutions might be setting C to San Francisco, L to San Francisco, California, and S to California. Okay, and the nice thing about having this kind of constraints formulation is that DCS trees are trees, and for trees we can compute this efficiently using dynamic programming in a basically the same as if we're doing the propagation on a tree. And the running time is the number of nodes. In general, it's obviously trees are hard, but since we're going to be building these trees, then it's going to be okay. Yeah.
Right, you lost me. What does L1 and L2 refer to?
So L is a tuple of two elements. L2 is a second component of L.
I said, and it's a tuple corresponding to that table?
Yeah, so this table, think of it as a set of tuples. This says, the constraint says that L is an element of that set. So L is any row here, and L2 is the second element.
And what does the 2 underneath the logo on the diagram mean?
So this is kind of notation for denoting the system of constraints. So this says that this edge introduces a constraint that this 2 is this 2 and this 1 is this. So if this is I, this is J, then Li goes as J. Okay, so you can now, this is kind of a tree for something a little bit larger, just to give you an idea of what these things are going to look like. So this is a city that's located in a state bordering California, and the city also traverses a major river that goes to Arizona. So as you can see with the beauty of compositional semantics is that with relatively limited means you can start developing rather complicated utterances. And just to highlight the fact that we're building these trees, and remember I mentioned that these kind of look like dependency trees in linguistics, and there's if you look at syntax, there's kind of only local relationship between the words. It's kind of syntactic dependencies, and it turns out that those same syntactic dependencies correspond to the tree structure, which are important for computation, as we saw as well. So trees are kind of a nice way to have an efficient formalism that has also expressive properties. Okay, so if everything were that simple, then that would be great, but language also always has a lot of complexities. And just to illustrate one of them, take this phrase, most populous city in California. So here's kind of its coarse syntax. So here's most populous, most is a modifying populous, which modifies city. But if you look at the semantics, I'm kind of writing it out in the lambda calculus notation. Here, that most corresponds to this argmax, and argmax is kind of way out in front, so on top. If you were to write this out in a tree, argmax would be kind of the root node, because it has to be applied last. But so the weird thing now is that if we're going to build trees like this, but we want to get the correct semantics, in which the most element is high up in the tree. So here's the syntactic position is low and the semantic position is high. How do we reconcile this discrepancy? So we have a solution to this problem in the context of our framework is what I call the marked execute. And the idea is, the intuitive idea is fairly straightforward. The idea is that we're going to build our trees which are going to look like syntax, but we're going to insert these kind of special mark relations which are going to say, hey, there's something, just hang on to that guy for now. And then I'm going to execute at the appropriate place where this element is supposed to take effect. So this tree, remember now it looks like this syntax tree, but it encodes all the information that you need to get the correct semantic reading out of it. So we kind of have our cake and eat it too in some sense. And so this is kind of a superlative construction. I won't go through the details, but this is kind of a general framework that you can use to handle other scope divergence problems like negation and quantification. And maybe it's worth going through this example. So this is kind of a canonical quantifier ambiguities example in linguistics, where you have some river traverses a city. It has two readings. Either there's a really long river that does a TSP, or every city there's a little DP stream that goes through it. And here we can see in this formalism, we don't have to commit to this when you're building the tree up. We always say is that sum is a quantifier, upper is a quantifier, don't do anything. And then up here we execute, and here we see that you specify the order. 1, 2 means that we're going to handle the every first, and then the sum, so you get a narrow reading. And if you swap, then you get the other reading. So this kind of is nice, because when you parse this, the two syntactically are the same, but you kind of localize the semantic impact in one place instead of several. And I should mention that this solution isn't. This is a whole problem, and a number of other linguistic. Basically every serious linguistic framework has to deal with these and other issues, and they kind of go by different names: quantifier raising, quantifying in, and Cooper storage, and so on. So I'm just presenting this in the context of this DCS framework. Okay, so that was a rough sketch of the representation. We're going to be trying to learn these trees. How do we actually do it? So here now I'm going to set up a probabilistic model. Before I showed you how you can take a logical form Z and a database and evaluate to get an answer, but I haven't told you anything about how it hooks up with language. All I said is that, yeah, it kind of looks like a dependency tree. But we have to do a little bit better than that. So this part is called the interpretation, and it's deterministic, but it's non-trivial. And now I'm going to focus on the other part of the picture, which is that you're given an utterance, capital California, and you want to map it onto the logical form with the aid of some parameters. So this part is typically called semantic parsing, and it's probabilistic because we're trying to, language is ambiguous, and we have to maintain uncertainty over logical forms that we might need. Okay, so now this is kind of the rough structure. I'm going to dive in by telling you what is the support of this distribution, essentially. What are the possible DCS trees we're going to consider for a given utterance, and then tell you about the actual details of the model. Yes, David?
Is your intention that you're going to be, I understand you're discussing a prior noun and sometimes over Z, but at test time, will you be doing this with respect to a number of candidate answers? So you have the aid of that evidence as well?
So I wouldn't exactly call this the prior, so this is the input. Think about it as a discriminative model. So here's the input, output, there's a latent variable.
So the answer is yes then, so you will be using it jointly?
Yeah, it'll be joint. Okay, so what are the possible trees? There's an infinite number of trees. We can't consider all of them, let alone marginalize out them all. So here, let me start with the example. What is the most populous city in California? So we want to define a set of possible trees we're going to place a distribution over. And to start out, for each word we're going to put some number of predicates. So this is kind of the initial word-to-word, word-to-predicate matching. So Ray would call this cheating, but it's not that bad. So for constants like California or proper names, you basically say, yeah, that looks like the California I have in my database, and you move on. So for function words, we're going to, because there's such a small closed class of them, we're just going to specify them, and that's going to kind of constrain the learning. And so now for, yes.
How about ambiguity?
And
how about ambiguity? Most could be.
Yeah, so the idea is not to pin down, at this moment, it's not to pin down the right word. It's just to give a candidate. So if you have other candidates, you just put them so in particular for nouns and adjectives, here we assume that we don't know what a city is. It could be, the string city could be a city, it could be a state, it could be a river, it could be the population or whatever. So we just write them all down. Okay, so now at this point, we have a list of candidates, and now we're going to build up the trees recursively. And this kind of follows kind of the rough flavor of kind of parsing in general. And the idea is that for every subspan of the sentence from I to J, we're going to have we're going to build a set of DCS trees. We're going to consider all split points K, recursively build the subtrees for those, and then take basically take the cross product and combine the trees in some local way. And then we generate a bunch of hypotheses for this tree, this subspan, and so on for that. Okay, so now we have to find the set of trees. We have to define a distribution over that. And here it's a relatively straightforward log linear model where we have the input sentence, we have the DCS tree which is built on top of it, and we just find some features. And these features are very simple ones which kind of are indicator of whether a word appears with a predicate or whether a predicate appears with another predicate via some relation. So there's a bunch of these simple things. And this is very standard if the log linear model is an inner product between the features and some parameters which we're going to learn. Okay, so learning is basically going to be maximum likelihood where we marginalize out the latent Z's. And here, one thing I didn't mention is that in practice, so this procedure for kind of building up trees can blow up quickly. It's a kind of exponential. So at each point in time, we're going to say, take the top 100 hypotheses and drop the others on the floor. Okay, so the learning works as follows. You initialize the parameters to something reasonable like 0, and then you use the procedure I described to enumerate the trees. And now you can, for each of these trees, you run them on the database and see, did you get the right answer? And you mark the ones that you did, and this gives you kind of, now not completely a supervised problem because there could be still multiple right answers, but it gives you kind of an unsupervised problem without the kind of the nasty search problem. So now you can optimize the parameters given this by just using kind of gradient-based methods. And then now you have some new parameters. When you explore the set of trees, you might get something different because the parameters have changed. Hopefully the good guys will go to the top and then you iterate until you converge. So I'm calling it an EM algorithm because it's not exactly EM. This part is kind of doing the gradient version of EM. This is kind of the structural. So I've broken it up into kind of the structural part and the numerical part. Okay, so on to experiments. So we experiment with this standard semantic parsing benchmark, which Ray and colleagues have developed supervision started using since the 90s, and it consists of examples that look like this. What is the highest one in Florida, and sentences, and each of them is labeled with a logical form in the original data set. But we're going to not learn from these logical forms, but instead learn from these answers. So to a learning algorithm is we have some training data, we have this lexicon. So there's two versions of this experiment. One is where we tell it that city is, so for every predicate we have one word that we know to be. So the city could refer to other things like towns or villages or settlements, but we just give it one kind of as an initial seed. And there's another version of experiments where we don't tell what city it is. And then we have the database, which is just kind of fixed for good. So in experiment one, we were trying to compare how well does our method work compared to other. So there's another system which also learns from question and answer pairs, essentially. And they use kind of a different framework, which I won't have time to go into. So they don't use logical forms, but they have this pretty elaborate lexicon. And we show that our system, despite using a kind of a smaller lexicon, can improve the results. And if we kind of use something comparable to their supervision, then we improve even more. So the second set of experiments is we're trying to compare to the state-of-the-art semantic parsers on this data set. So in particular, these are going to use logical forms as supervision. So there's been a lot of work on this. I'm showing kind of a subset of this, which is more directly comparable. So there's this line of work by Luke Warner and Mike Collins and some of their colleagues, which are able to learn using logical forms, but importantly they learn the lexicon, and they are able to get something like 88.9. If we learn with a small amount of lexicon but no logical forms, then we do a little bit worse but comparable. And I just want to point out that the logical forms are those. Remember, those are those complicated things which would be hard to get a human to annotate, whereas the lexicon is saying that city is city. So I think it's less supervision. And if we allow ourselves to tell it that city is city, so there's 75 words, then we get an improvement on that. Okay, so let's see. So this is, I guess, the point of the take-home message is that even though we have this huge, nasty logical form as a latent variable, we show that with kind of sufficient representation and some constraints from the lexicon, we're still able to learn and pretty effectively. Okay, so so I mentioned before that there's kind of an intrinsic hard search problem, which is that, especially in the beginning, your parameters are 0, you have no idea what the semantic parse of a sentence is, and you're supposed to get the right answer. So it's a very nasty combinatorial search problem. And in the beginning, it's so hard that you might come across a sentence and you get your top K list, and there's nothing that is you are unable to get the right answer. In that case, you skip it. But we see that as you train, so after the first iteration, you're skipping something like 70% of the examples just because you can't do anything. But when you train on that 30%, you get improve your parameters, and next time you're able to train on 60%, and it converges to something like 98%. So you see that there's this kind of almost automatic curriculum learning where in the beginning, you don't know anything, so you train on this 30% are the easy examples where you can just kind of brute force search it and you get the right answers. And these you learn some nice parameters, so that enables you to bootstrap up a more accurate model. Okay, so I'm going to go through this quickly. So this is kind of current limitation slash future work. So currently we're thinking of the program as a black box where we only execute the program, get the answer. But really this problem is about inverting a program, going from the answer back to the logical form, and it might be useful to exploit some more rich properties of the program. Let me skip that. So all of this is constrained by the database, so there's facts. If you ask how far is Los Angeles from New York, the database currently has no database. Distance information, so we'll be able to handle it. And there's also unknown concepts, which are what states are landlocked. Even if the database has that information, landlocked is something that's not just a predicate in the database, but it's kind of not bordering the ocean. It's something more complicated. And there's words if you never see settlement in the training data, then you might not be able to get that right. Let me just show you that for these last two, we can actually do a little bit more. So let's say, what is the largest settlement in California? Oh, shit. I wanted some of this was going to happen. Yeah. So it wasn't my code, it was the JVM. The JVM's been kind of crashing. So the idea is that, let me just do this. So what is the largest settlement in California? And it's never seen settlement before, so all these weights are 0. And it basically tries the best guess. And it decided, well, I'm going to tell you the longest river instead, which is the Colorado River. But if you want a feature of the system is that you can go down here and look at the candidate answers, and you see that, what was the question? What was the largest settlement? Okay, so that's Los Angeles, and here's Los Angeles. You click on it and say that's correct. And now what this does is it gives a training example to the system, makes an online update, and now if you ask, and hopefully it won't crash, then it'll give you the right answer. But more importantly, it kind of generalizes. So you can say what settlement in Texas is the largest. And good. We're from Texas. Okay, so it does a good job of kind of generalizing from that one example for this case. There are other things. What if you want to know what is the largest settlement in the Pacific Northwest? Okay, well that was clearly wrong. And what happened here is that Pacific Northwest it's one of these kind of more advanced concepts. It's not a city thing, and the system doesn't know anything about it. But fear not, we can do. So what is the Pacific Northwest? Well, it's kind of like Washington State and states bordering Washington, right? And we can say that's the Pacific Northwest. Now if we ask what is the largest settlement in the Pacific Northwest, it's able to use that piece of information and tell you that Seattle is the largest city among those 3 states. Okay, so my slides disappeared. Okay, so let me conclude now. So we start with the problem of semantic interpretation. I try to argue that this requires, kind of a more complicated program representation. You can't just get by matching words. On the other hand, we want to be able to learn these representations from natural supervision. So, which means we're going to be dealing with this hard learning problem with a large link variable. And we saw that from a learning perspective, there's kind of several interesting things I want to point out. One of them was this kind of automatic curriculum learning, I think, which really helped in this case, because in the beginning, your model is really bad and you have no idea, so you can kind of only rely on the simple examples to bootstrap yourself up. And this kind of, I just showed you is, I think the online learning is a promising avenue, where imagine you have a system which is doing online learning and it's also online. So users can interact with it, and if you're not getting the right answer, they can give immediate feedback. And in this manner, you could hope to train up and bootstrap a more better and large-scale semantic parser that answers questions. So just kind of finish off with the cartoon picture of where I see all of this. So, back in the good old days or bad old days or whatever, there is a lot of emphasis on getting a lot of depth out of language, but not in very limited domains. And over the years, the statistical revolution has pushed us in this direction where we're able to parse the entire web, but we're not doing any sort of understanding nearly as deep as before. And you can see this work as, obviously we want to go into the upper right corner, so the challenge will be to how to bridge these two, and this work represents kind of one little inch in that direction. Thank you.